Hello and welcome to Introduction to Business Finance, Chapter 8B, More Time Value of Money. We're going to start this section by looking at projects with multiple future cash flows. So far, what have we done here? We've been looking at projects with one future cash flow that have a cash flow diagram that look like this. Starting at t=0, that's what we call the cash flow at the present time. We have one cash flow, and then some time elapses, and there is a second cash flow. So total number of cash flows in the problems we've been doing so far is 2, and we can also describe them as one future cash flow types of problems. Also, FYI, some folks call these lump sum problems. So it's probably good to know all three phrases: 2 cash flow problems, single future cash flow problems, and lump sum problems. So in the real world, most problems actually involve multiple future cash flows. And happily, these sorts of financial problems are solved easily by treating them as sets of 2 cash flow problems. Let's look at an example right away and see how this works. So let's find how much would an investor pay to purchase a CD that returns to them $6,000 in 1 year and $8,000 in 2 years, and the interest rate on this CD is 10.4%. So let's start out with a cash flow diagram for this investor. So I'm reminding us up in the top here that our interest rate is 10.4% for this problem. And for this investor, the initial cash flow is going to be negative. So we have a cash flow going down here, and we're going to call this CF0 or PV tote. And then this contract says that for the total amount the investor puts in down here, that she's going to get back $6,000 in 1 year, and then a year later she's going to get $8,000 back. So that's the situation graphically that we've got for her. And the CF0, again, is what she pays now, but we can think of that like this. Part of what she pays right now is a blob or a tranche that is going to grow to $6,000 in a year, and another portion of what she puts in at t=0, or another tranche, is going to grow to $8,000 in 2 years, and the interest rate for each tranche or each blob is 10.4%. So then her total amount of CF0, the total here, CF0 or PV tote, is going to be equal to tranche A plus tranche B, or blob A when blob B. So let's go back to one page before we continue too much here and write in on the cash flow diagram the way that this is working. So we'll call that piece A, and we'll call this piece B, and let me just do something here, switch back over to the typewriter, and let's call this A, and let's call this B. And what's going to happen is that A plus B is equal to CF0 equals what we can call PV tote for a present value of the total amount that she's going to have to pay now. And then what does she get for that? She gets chunk A, tranche A, blob A, however you want to think about it, grows into $6,000 in a year, and blob B or tranche B grows into $8,000 in 2 years. And again, we know that each of these blobs is growing at 10.4%. So let's highlight that too. So now we have a really good framework for solving this problem because we can just solve it one piece at a time. Let's see how that works here on the next page. So for tranche A, we know that the PV of A is equal to the FV of A divided by 1 plus R raised to the 1, because that's just growing for 1 year. And so that PV of A is equal to 6 divided by 1 plus 10.4% raised to the 1. All right, and we can do the same thing now for piece B over here and say that the PV of piece B is equal to the future value of B divided by 1 plus same R raised to the 2, and that is equal to R8 divided by 1 plus 10.4% raised to the 2. Okay, and if you work these out numerically, I'm going to sneak here and look on the next page. We get 6.56 for the second one here. And all of these numbers are in K, so I'll just remind us of that there. And then for the first one, we can, if you don't want me to cheat, it's fine. I'll just throw this into the electric pencil. And we get 5.43K. So the total here is going to be equal to A plus B. So that's 5.43, whoops, yeah, 5.43K plus 6.56K. And we add that up and we get 11 point, it's looking to me like 99K, and we'll call that 12K. Because we have some rounding in there and all that jazz. Okay, so let me just scroll back to this just for a second here. So all we did here is we know there's a total amount that the investor has to pay to get in this contract to get back 6,000 in a year, 8,000 in 2 years, and we know that in the contract it says her money will be growing at 10.4%. So we just took one piece at a time and used our fundamental time value equation to get the present value here of this 6,000, and then we did the same thing with our fundamental time value equation to get the present value of this piece here, and we added them together and wound up with 12K. So now let's see if we can generalize from that example and get an equation and some verbiage that we can use for any problem that we see like this. So in general, what we could say here is that the total present value, which we'll call PV tot or CF0, of a set of future cash flows is equal to the sum of the individually discounted cash flows. All that means, all that's saying is that we discounted that future value, that 6,000, and we discounted that 8,000, and then we added them up. So we discounted each one individually first, and then we added up the discounted value. So that's all that's saying. And now, if we want to throw some math into it, we could say for a set of future cash flows, CF1 through CFN, we could say that the total present value of all those cash flows, or the CF0 of all those cash flows, is just the present value of the first one plus the present value of the second one, plus et cetera, et cetera, et cetera, of the present value of the nth or last one. So now we can put that mathy notation into summation notation, which just makes our life a little simpler and makes it easy to represent all kinds of problems. So to say this with summation notation, we'd say the present value of a bunch of future cash flows, which we'll call CF0, is just equal to the sum of every stinking future cash flow individually discounted back to t equals 0 and then added up. So that's what this is telling us. I is equal to 1 to the number of cash flows n. So we're going to do this with every future cash flow from 1 to n. And ti is the time of that cash flow. And we always say t equals 0 at our PV time. This equation is so important that we're going to call it the fundamental discounting cash flow equation. So now we have two super important equations here. We have the fundamental time value equation, and we have its sister equation, the fundamental discounted cash flow equation. So how should we think of this? Let's do what we did with two cash flow problems and look from a lender's perspective and also from a borrower's perspective. Starting with a lender's perspective, so this would be a CD investor. If you're a CD investor, you're a lender, you're loaning your money to that CD company. We'd say that PV tot is the amount that we invest now, or we could say the principal that we commit now to receive the future stream of cash flows. The second thing we could note here is that if we hold the amount we can invest constant, let's say we can only invest $10,000, as the interest rate we charge as the lender goes up, the future cash flows that we get go up. And that leads to a very good concept question, which is, should we try to maximize R? And I'm going to go ahead and answer this for us. So I'm going to say no for two reasons, okay? So reason number one is our competitors will undercut us. Finance is a very competitive business, and if we're out there charging way too high interest rates, our competitors will come in with slightly lower rates and just get all of our potential customers. And our second reason here is that any customers we do get will be very risky. So if we have a customer who has previously gone bankrupt 3 times before, our competitors are probably going to say, we don't want to do business with you, and they'll come to us even though we have very high interest rates because no one else will do business with them. So for both of those reasons, it's not necessarily great to try and maximize our interest rate. Now let's look from a borrower's perspective. So this would be, using our above example, the CD purveyor. So in this case, for the CD purveyor, CF0 is the amount we can get now from one of our investors if we agree to pay the future stream of cash flows. And usually when we're a borrower, our limiting constraint is our future cash flows. How much can we pay back a year? Can we pay back 10,000 a year, 20,000 a year without going bankrupt? That type of thing. So using our maximum future cash flows, the future cash flow is held constant. As the interest rates go up, the amount of money that we can get at t equals 0 goes down. So we, of course, would like to have, as borrowers, as low an interest rate as possible. So that leads to the question, and let's think of this just from a consumer's perspective here. As a borrower, how could we reduce the interest rates that we have to pay? And that the primary answer to that question is to get a good credit score. Even if we are starting a business or something like that, when you're just starting a business, lenders are going to look at your personal credit scores and borrowing histories to get an idea of how you're going to perform in the business world based on how you have performed as a consumer. So, hot tip here is it's a good idea to get a credit card, and very occasionally don't pay the full thing off, and then be sure to pay it all off in the next 2 or 3 months, something like that. You do that 5, 6, 7, 10 times, and now you have a record with that credit card company of having taken out a bunch of small loans and paid them back on time, and that will start to give you a good credit score. Let's do another example. So Velocity Advisors is back in action, and they're offering to pay you $6,000 at the end of the next year and $12,000 a year after that in return for your payment now of CF0. And the interest rate on this deal is 10%. So let's see if we can find out a bunch of stuff about this. First of all, let's do a cash flow diagram for us. And we want to find CF0, the amount that would have to be invested now to get that beautiful $6,000 in a year and $12,000 in 2 years. And then let's answer the compelling question. If we just have $15,000 to invest now, can we participate in this deal? All right, so let's go ahead and take these one at a time. So we have a cash flow diagram, in this case, that looks just like this. We're starting at t equals 0 with making an investment. This is going to be negative, right? Negative for us, because in this case, we are the lender, right? All right, so this diagram is clearly for lenders. Lenders always have that negative cash flow at t equals 0. That's the total amount that we're investing now to get the 6,000 in a year and the 12,000 in 2 years, with our money growing at 10% annual compound rate. Okay, so a good way to word this is CF0 is the total amount we pay now that's going to be growing at 10% annually and repaid in 2 blobs or tranches, a blob of 6,000 at end of year 1 and a blob of 12,000 at end of year 2. So now we can go ahead and calculate this the same way we did before. I'm going to draw this in again here, pretty much like we did before. And again, I'll just call, well, let me do this. It's going to be the present value of the first one. And here is the present value of the second one. And so I'll call this A, and I'll call this B. And A is the present value of the 6K. B is the present value of the, 12K. And if we add those together, A plus B is equal to CF0 or PV total. So it's really that simple. So let's go ahead and do those calculations on this next page here. So we have 6 divided by 1.1 raised to the 1 plus 12 divided by 1.1 squared. And if you work that out, you do get 15.37. And again, our units are K, and I'll put in some dollars. Okay, and just to key this to the diagram on the previous page, this would be A, and this would be B. And this is the PV of 6, and this is the PV of 12. And it's really that simple when we have multiple future cash flow problems. So that's pretty great. All right, so I know that some of you skeptics out there are saying this guy is king of all typos. I don't believe his calculation. Well, there you go, 15.37. All right, so like we were just saying, the CF0 includes a portion corresponding to the first repayment and a portion corresponding to the second repayment. And I'll let you read this to reiterate what we just said. Okay, so now how much do we have to invest here? So can we do this deal? Let's see. So we just have 15K to invest. And to do this deal, we just saw we would have to pay Velocity $15,370 to make this deal work. So the answer to that is no, we cannot participate. And that's because we have just 15K, excuse me, but need 15.37K to participate. Okay, let's look at another example. Zero Motorcycles has a model called the Street Fighter S, and you can buy it at Amazon for $9,000. You could also buy it from Rent-A-Center, and they're offering the same bike for 0 down and 2 uniform annual payments of $6,000 starting 1 year from now. Your bank gives you 10% annual interest on your savings account should you buy the bike from Amazon or Rent-A-Center. And why? Assuming for the Rent-A-Center option, you'd be investing enough now in your savings account to make the 2 future payments. So this is going to be, again, find the PV tote or the CF0 for the Rent-A-Center option and see how that works out. So let's go ahead and do this. So we have 2 projects to compare here. The Amazon project, we just go back and say, all right, we can buy this now at t equals 0 for 9,000. So our CF0 for the Amazon project is 9K. That's all the cash flows that we have. We have that 1 negative cash flow to Amazon, and we get the motorcycle, and we're done. The Rent-A-Center project is more complicated. We're going to have 2 blobs of cash that we're going to put into our 10% savings account now. So blob 1 is going to grow at 10% to 6,000 in a year, and blob 2 is going to grow at 10% to 6,000 in 2 years. And then the total amount we have to set aside now to grow into those 2 payments is blob 1 plus blob 2, or PV tote, or CF0, comma, Rent-A-Center. Okay, we can do this now very easily, right? I've just got to get the present value of that first 6. So I have 1.1 raised to the 1. And then for the second one, I have again 6 divided by 1.1 raised to the 2. And let's see what that turns out to be. So I'm going to go ahead and throw this into the electric pencil over here as well. Blammo. Okay, so I get 10.4. So we'd have to put 10.4 thousand aside right now, excuse me, in our 10% savings account. So that would grow into, a portion of it would grow into 6,000 in a year, and another portion would grow into 6,000 in 2 years. Okay, so definitely buying from Amazon is best because for the Amazon option, the PV tote equals CF0 equals 9K, and that's it. And for the Renter Center option, the PV tote equals CF0, which is equal to 10.4K. And that, in most circles, is more than 9K. Okay, let's look at another example with Shady Deals Inc. So they're offering to pay you $6,000 1 year from now and $12,000 2.5 years from now in return for your payment of $14.91 thousand. So Shady Deals interest rate on this project is R. Let's see if we can find for this one a cash flow diagram for you, an algebraic equation to use as a start point for finding R, and then is R closest to 6%, 10%, or 12%. So R, of course, as usual, is the annual compound interest rate for this deal. So for the cash flow diagram, let's remind us of what we need. 6 in 1, 12 in 2.5, 14.91. So let's draw a cash flow diagram. So we're going to put, as usual, time on the x-axis here. And then let's start with our initial payment of 14.91. And here's the 6 we'll be getting in a year. And here's the additional we'll be getting in 2 years. Everything might not be perfectly to scale, but it's good enough for our purposes here. Let's see. Nope, that doesn't work. All right. Let's fill this in here. So this is time t equals 0. This is time t equal 1. And this is time t equal 2. And here's our 6K. And here is our 12K. Okay, and to make this all happen, we're going to need to pay right up front 14.91K. And as usual here, we're going to have that 14.91K made up of these two pieces here, right? And we've got piece number 1 is going to be growing to 6K, so we could work back to its present value like that. And the second piece is going to be growing for 2 years, so we could work back to its present value like that. And if we wanted to, we could call each tranche or each blob here respectively A and B. So I think that's pretty good here. And I would also want to point out that what we're looking for here is what's the R? And I'm not quite sure of that. So let's see if we can work it out together. Okay, so that's pretty much it for our cash flow diagram. Let's see if we can move on now. So now what we want is an equation that we can use as a start point for solving for R. As we saw in the problem statement and the cash flow diagram, everything is known except R here. So we're going to use our fundamental discounting equation here, and we'll go ahead and expand that out, writing in everything we know, and hopefully everything but R is going to be there. So I'll start with the left-hand side. So I've got my 14.91, that's our PV tote, is equal to, so my first cash flow I here is 6, and that's going to be divided by 1 plus R raised to the 1, because that's the cash flow we'd get in 1 year, plus 12 divided by 1 plus R raised to the 2.5, because that's the cash flow we'd be getting in 2.5 years. And I think that's it. That's good enough. This is a very nice equation that we could use as a start point for finding R. And we might want to note, those of the in-the-know mathy folks amongst us, that we can't solve this equation for R. The quadratic formula is not going to work. To solve this, we'd have to find the roots of what we call a real equation, which requires numerical methods. All right, so now let's move on to figuring out if R is very close to or equal to 6%, 12%, or 10%. So the way to do this is literally just to plug in, right? So if R is equal to 6%, what we get is 6 divided by 1 plus 6%. And we could raise that to the 1, but we know we're doing that, so I'm not going to worry about that. Divided by 12, plus 12 divided by 1 plus 6% raised to the 2.5. And let's see what that turns out to be. Okay, and that's 16, so that's no good. And that's not equal to, in most circles, 14.91. So we conclude, okay, what we're looking for is right-hand side equal left-hand side. We want R that makes right-hand side equal left-hand side. All right, so I'll leave it to you to go ahead and do this yourself with 12%. So I'm going to plug in 10%. Okay, and let's see if that is equal to or close to 14.91. Oh, look at that, 14.91. Okay. Okay, so this does equal the left-hand side. So this is it. Okay, so we can conclude that R for this deal is equal to 10%. So you should know that on an exam, this would be a great exam problem, a sort of two-part problem where number one, you set up the algebraic equation to solve this, and you just want to plug in everything you know to the fundamental cash flow discounting equation. And then given some multiple choices here, which is the correct R? And on an exam, I wouldn't want to give you more than three, so it doesn't take too much time to check. Okay, a little more stuff for the finance majors and also the math-oriented folks amongst us. And now back to everyone, a little bit more on time value and risk. This is a review, but it's very important to know, so I want to reinforce it. So in general, we know that interest rates increase with a project's risk. And this is not true because there's any law of finance that makes it true. It's true because we see it to be true in nature and in finance and financial markets. So implications of this are that the Treasury can borrow money at something like the lowest interest rates around, and that's because we know they're considered risk-free with all the caveats that means, and subprime borrowers pay more interest to compensate for the higher probability they will default. So the key takeaway on this page is that the riskier the project becomes, the higher the interest rates investors demand to participate in that project. And that's something that's going to be good for us to know for the rest of the term. So now let's move on to a new class of projects. These are constant future cash flow projects, which are also very often called annuity projects. So the key characteristics of this are that all of the future cash flows are of the same magnitude. And they have a common interval in time in between. So you can see that very clearly in this cash flow diagram here. The magnitude of the first future cash flow is F1, F2 is the same as F1, et cetera, et cetera, et cetera. So let's go ahead and put that in here. Whoops, there we go. So let's say F1 is equal to F2 equal to comma, dot, 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 equal to Fn. So all of those future cash flows, same magnitude, and the interval in time between them all remains constant. This is a very important class of projects because it's the way that mortgages work, it's the way that financial annuities work, it's the way that annuities do or leases work, and perpetuities, and all sorts of other things, but not growing perpetuities. So let's look at the math involved for these things, and then let's do a bunch of examples. So remember our general case here for a multiple future cash flow project. The PV tote, or the CF0, the amount that the lender is going to invest now at t equals 0, is equal to the sum of every stinking future cash flow individually discounted back to t equals 0. And that's what's going on with our fundamental discounting equation here in summation notation form. So in our case, all of these future cash flows are identical. And then through the awesome power of algebra, we can simplify this equation a little bit by pulling that constant uniform cash flow outside of the summation. That makes life a little bit easier for us. It makes it possible to solve for this, for example. So it's a nice way to have this. Because this is so useful, we're going to enshrine this equation with the compelling identifier 74D. Also, we can find a closed form, that means finite term, algebraic equation to help us solve for this. So here's the way you'll see it in textbooks. PV tot is equal to C. C is that constant cash flow that we're very often going to call CF, times this big whole mess in it that has our interest rate R in it, and N in most textbooks means number of periods. It's also the same thing that we'll call T, right? We have 12 years, 12 periods, that type of thing. I like to rewrite this equation the same way you would type it into Excel or a calculator. So I prefer to write this equation just like this. What I find, and what I find for many students, is when you try to translate from the textbook looking version into your calculator or Excel, you very often make mistakes. And if you use this version, it's actually a lot harder to make a mistake. And so we're going to call this 74E. And we have some rules down here of the use of 74D and 74E. 74D, which is this guy over here, it's just a slightly modified form of our discounted cash flow equation. That's going to work for any constant cash flow project, any annuity project. 74E, we have to remember, has some restrictions. So this is going to work, this equation is going to work for any constant cash flow project except annuities due. And we're going to have an equation called 74F for annuities due, which is presented around page 51. So we'll get to that later. All right, so let's look class by class at the types of classes of financial projects that are constant future cash flows. Let's start with type A, and that's mortgages. So let's consider a 3-year mortgage. So we're starting off here with Mr. Small Net Worth. Mr. Small Net Worth wants the biggest 3-year mortgage he can afford to help him buy the biggest shack that he can find. And so he goes to a lender. One of the first things a mortgage lender will do is ask the question, how much can this potential customer afford to pay back per year without going bankrupt? And that's going to set the size of the mortgage they'll give them and everything else. So the lender Mr. Small Net Worth goes to estimates that Mr. Small Net Worth can afford to make mortgage payments of a little bit more than $12,000 a year without going bankrupt. And they do that by looking at his salary, his other expenses, et cetera, et cetera. And the lender's policy is to charge 10% compound annual interest to borrowers of Mr. Small Net Worth's credit quality. So with all this great information in hand, let's see if we can find out how much will the lender let Mr. Small Net Worth borrow. So let's define some terms and get a cash flow diagram to get us started here. So let's say that CF0, as usual, that's going to be the amount the lender gives to Mr. Small Net Worth, and that's always at T equals 0, the beginning of the project. And the way these mortgages work is that all of Mr. Small Net Worth's future payments, payment 1, payment 2, payment 3, are going to be constant. So we can just call them CF. Okay, and we know the amount of that CF. At the end of year 1, 2, and 3, the CF that Mr. Small Net Worth is going to pay is shown down here on the cash flow diagram, and it's $12,060 here. So we have always helpful to have a cash flow diagram here, and this cash flow diagram is clearly for the lender, right? The lender always has a negative cash flow in the beginning, and they get positive cash flows later on in the project. And by the way, the total cash flows that they get later in the project, forget time value of money, they better add up to more than the lender puts in at T equals 0. Otherwise, you have an incredibly stupid lender, or you've made a mistake in your calculation somewhere. So what's the CF0? What's the dollar amount for the lender? It's the present value of the first cash flow plus the present value of the second one plus the present value of the third one. So as usual, the total amount looks something like this, right? Where we have the total CF0 is made of these 3 blobs that look like that. So to put that in words, at T equals 0, the lender wants to loan a tranche that's going to grow to $12,060 in 1 year, and loan another tranche that will grow to $12,060 in 2 years, and another tranche that will grow to $12,060 in 3 years, and the sum of all 3 tranches is equal to CF0 or PV tot. All right, so let's solve this using both equations 74D and 74E. So 74D, remember, is just our slightly modified version of the fundamental discounting equation here. And let's see what we can say about this. So we know the future cash flow, it's equal 1, 2, and 3, and we know the interest rate. We also know that R is equal to 10%. Okay, and algebraically here, let's go ahead and put this in. So CF0 equal PV total. Let's just do it completely algebraically to start. So I'm just following this equation exactly for our 3-year mortgage. So I'm going to have 1 over 1 plus R raised to the 1. That's going to be for the first payment, plus 1 over 1 plus R squared plus 1 over 1 plus R cubed. So that's what we've got algebraically. Now let's plug in all the numbers that we know. We know that CF is 12,060. We know that R is 10%. So I can say 12.06 times our 1 over 1.1. Let me simplify that a little bit. 1 over 1.1 plus 1 over 1.1 squared plus 1 over 1.1 cubed. And that's it. That's going to total up to what Mr. Small Net Worth, what the lender is going to have to loan to Mr. Small Net Worth at the onset of the mortgage. So we put that into our electric pencil and we get 29.99. Let's just call that 30.0. Okay. All right, so if the lender agrees that Mr. Small Net Worth is going to pay back $12,060 for the next 3 years, at the end of those 3 years on a 10% mortgage, then the lender will loan to Mr. Small Net Worth at T equals 0 $30,000 to help him buy the shack of his dreams. So now let's go ahead and solve this with our closed form version. And again, I'm going to choose to use this version because it's too easy for me and by experience, many students to translate from this into a calculator. Making mistakes is the common result. So I'm literally just going to follow this, putting everything I know in. So let me go ahead and highlight that with an arrow. And here we go. So the CF is 12.06 times 1 minus 1 plus, we know R is 10%, 1 plus 10%, raised to the N is the time period for the mortgage. That's 3 years, so raised to the minus 3 and divided by 10%. And I better get 30 for this, or I've made a mistake either here or in my prior calculation. Okay, and I get the same thing. So we have 30. Okay. So very straightforward. Either way is going to work for us with these constant future cash flow problems. This one is going to work for everything except annuities due, and we'll have another equation for that. And so this is 74E. And 74D, we could also solve it with 74D up here, and that's going to work even with annuities due. And at that point, I think this is a good place to stop for the week, and we'll pick it up next week with constant future cash flow type B financial annuities. So have a great weekend, and I'll look forward to catching up with you soon.